All right, so in terms of the timeline for this week, today is the last lesson for momentum, and then I posted on the files tab a review. What's it called again? It's like Momentum Provincial Package or something like that. So it's just a package of past provincial exam questions on momentum. So you can go through that. And I think I'm gonna. I said Wednesday, I think. Yeah, I'm pretty sure I said Wednesday, but I'm thinking of making the test tomorrow instead, like posting it after class tomorrow. That way you can work on the review today and then ask me questions tomorrow, and then I'll post it tomorrow. And then hopefully I can mark it like Wednesday morning-ish, because our marks are due Wednesday. And so then I can include that in your marks as well. So yeah, and that just gives us more time for circular motion as well, which is different. But I might, sorry, my wife just started the vacuum and it's really loud. I might actually post a lab for this unit. I'll message you guys later today explaining what I want to do, because I haven't really thought this through yet clearly. Okay, so before we get to any of that, are there any questions from any of the worksheets?
Yeah, I have a couple of questions from the worksheet package.
Okay, no questions. Okay. So today we're going to talk about specifically explosions, and then we'll do another angled collision, but this time it'll be an elastic collision. So just in terms of, oh, here we go. What's this? I have questions. Okay, perfect. From the worksheet package. Do I have the worksheet package here? Oh yeah, I do. I cannot hear you, no. It says you're muted though.
Can you hear me now?
There you go. Now it says you're not muted.
Can you hear
Still
me?
can't hear you though.
Okay.
I had this issue the other day with another kid. Apparently Teams is having like massive issues right now, so maybe this is maybe we're experiencing that. You can just write down in the chat what questions. Number 9 from worksheet 3.4. 3.4. Where's 3.4? 4.3? That would make more sense. Yeah, 4.3. And number 5 from 4.4. Okay. Which 4.3? Impulse or conservation of momentum? Assuming it's gonna be impulse. Okay. So that's this one right here. And then number 5 on the next one. Oh, I'm using that pen. Let's go blue. Okay, a 500 kilogram, oh boy. Okay, a 0.5 kilogram object is thrown vertically upward with an average applied force of 8.2 newtons by a student. Forces applied through a distance of 1.5 meters. What is the average net force acting on the object? Applied force. Okay, so the net force, if the student is pushing up with 8.2 newtons, and there's a force of gravity of 0.5 times 9.8, so 4.9 newtons, then the F net is going to be 8.2 minus 3.9, so that's 3.0, 3.3. 3.3 newtons. And then what is the velocity of the object when it leaves the student's hand? And so initial velocity is 0. Okay, so we could do this two ways. We could go m delta v equals f net times t. And what this actually is like, if you think about f net as ma, then we have m delta v equals mat, and the m's will cancel out. So we have vf minus vi equals at, which is one of our formulas anyways. But we don't have our acceleration, so that's why we're going to use the f net. So 0.5 times, and then vi is 0, so I'm just going to write vf equals f net. Oh, we're going to need time anyways. Okay, we're going to use time. Okay, we have to use kinematics for this. So vi is 0, d is 1.5 meters. If the f net is ma, then 3.3 equals 0.5a. So a is 6.6. And then we can find our t. So we're going to use d equals vit plus 1/2 at squared. This is 0. 1.5 equals 1/2 times a, so 3.3 t squared. Oh crap, my calculator's upstairs. Oh look, a calculator. You know what, I need to get my other calculator. Give me 1 second. Okay. You know what? We're totally wasting our time here. I can just use kinematics to find VF. I don't even need to find time. If we're using kinematics anyways, may as well just do VF. So VF squared equals VI squared plus 2AD. This is 0, so VF equals square root of 2 times 6.6 times 1.5. 2 times 6.6 times 1.5. Square root that. And we get 4.4 meters per second. Whew, okay. So that's that one. And you're probably asking because you have to use kinematics and we haven't really gone over that. So yeah, hopefully you've printed out the worksheet or sorry, the formula sheet, or you have it handy or on your screen or something like that, so you can see the kinematics formulas that you have to use. Okay, and then number 5 from 4.4. So is there 2 4.4s? No. Okay, number 5. Okay, so that's a very fast waddle. Okay, 15 kilogram penguin waddling east at a velocity of 7 meters per second. Collides with a stationary. So we have, here's our P1I of our initial penguin, P momentum penguin. And then P2I is 0 because it's a stationary penguin. After the collision, the 15 kilogram penguin is traveling at 4.2, 20 degrees south of east. So that's going to be something like that. And this is going to be 15 times 4.2. And then this is 20 degrees. Okay, so if you look at the actual formula, we have two objects, P1I plus P2I. And then afterwards we have P1I plus, or sorry, P1F plus P2F. We know what this is. We know what this is. This is 0. And so we can solve this for P2F. So P2F equals P1I minus P1F. Okay, so if we're doing that, we're going to go P1I, which is 15 times 7. 15 times 7, 105. And then plus negative VF or negative P1F. And so instead of going 20 degrees south of east, we're going 20 degrees north of west, which is, I totally drew this wrong. So there's our 105. And then we're going up like this. And this is 15 times 4.2. So that's 63. So let me draw this arrow a little bit bigger. And then this is going to be our P2F. Okay, and this is 20 degrees. So then we're going to use cosine law. So 105 squared plus 63 squared minus 2 times 105 times 63 times cos 20. I wish there was an easier way to do this. I've looked on my calculator for like a short way to do it, but there isn't. 105 squared plus 63 squared equals minus 2 times 105 equals square root 50.6. So this is going to be 50.6. And we want to know, so that's the momentum. And we want to know its velocity. And so we're going to take this, divide it by 10, because it's 10, like 50.6 kilograms meters per second, divide by 10 kilograms, and you get 5.1 meters per second. But we need this as well, that angle. So we're going to go sine theta over 63 equals sine 20 over 50.6. 3 sine 20 divided by that second sine. 2.4 degrees. What? Okay, let me try that again. I think I made a mistake. Yeah, there we go. Okay. Theta is 25 degrees. So this is 25 degrees north of east. Okay, and that makes sense because if all your initial momentum is in the x direction and you have if you have some going down towards the south, you have to have some going to the north in order to cancel that out. So that's why. Is the collision elastic or inelastic? Okay, so in this case, we have to figure out if there's any kinetic energy lost. So we're going to deal with the kinetic energy of the two penguins before. So 1/2 mv squared of the first penguin. The second penguin isn't moving, so I'm not going to do it. Plus 1/2 mv squared of the first penguin after the collision, plus 1/2 mv squared of the smaller penguin after the collision. So get rid of the halves. So we have 15 times 7.0 squared equals 15 times 4.2 squared plus 10 times 5.1 squared. Okay, and so the EK before the collision is 735, and I cancel the half, so it doesn't really matter, times 4.2 squared. This is 264.6 plus 5.1 squared times 10. Whoops, I did 50.1 squared times 10. 260.1. And so we have on one side 735, and on the other side we have 524.7 or 525. And so 735 minus 525 is 210. So there's 210 extra at the beginning. So there's definitely energy loss. Now, because I got rid of the 1/2, I got a different answer than that, but I got, what did I get? 210, which is almost half of that. I'm sure there's some rounding things in there, but you can, it doesn't matter. If you notice that after the collision it's smaller, then there was energy loss and EK wasn't conserved. So that means it's inelastic. Not 100% inelastic, but still it's not considered elastic, because in an elastic collision it has to be 100% conserved. Okay, any other questions? Maybe from the other worksheets? And I can't hear you, so you just got to put it in the chat. Okay. Let's do the notes. Okay, explosions. So we have kind of three different scenarios here. We have two objects, like they collide and they don't stick together. And then we have two objects and they do stick together. So you have one object after the collision. In explosions, we have an initial object with some momentum, okay, and usually it's 0, but it doesn't have to be 0. It could be moving already. And that is equal to, like, that one object explodes into many or becomes many objects. So we have P1F plus P2F plus whatever, however many objects we have, okay? And whatever you have before, the momentum before, is equal to the momentum after. So there's typically two types of questions we ask. There's recoil questions, where it's like the recoil speed of a gun or whatever, shooting a bullet or something like that. And then we have like explosions, like in this one we're exploding a pumpkin or a watermelon, I think. Yeah, watermelon. So let's do recoil first. A 12.4 kilogram shoots a 40-gram bullet at a speed of 500 meters per second. So what is the recoil speed of the gun? So assuming that the gun is at rest before it shoots the bullet, we have this initially, our PI is 0. And then afterwards, so like if you were to draw this, that's a great gun. Okay, there's your gun. And then you're shooting, like, the bullet's in the chamber. And then as the bullet goes that way, okay, the bullet's going to go that way. The gun has to go that way in order, because you can't create forward momentum without having some backwards momentum to counteract it. If you start at 0, you still need to end at 0. So initially it's 0, but then you have this P. I'm going to call the bullet P2F and the gun P1F. Okay. Now, technically, the gun has the bullet inside it. So this 12.4 is the gun with the bullet inside it. But because the bullet is 40 grams compared to 12.4 kilograms, that's not going to change the mass at all. So we're just going to take the mass of the gun as not changing. It's like the mass is insignificant, so we don't really care about it. So in order for this to be true, we have this, and then P1F plus P2F. And so P1F is going to be the mass of the gun, so 12.4 times its velocity. plus the mass of the bullet times its velocity. So 0.04 kilograms times 500 meters per second. And this has to equal 0. Okay, so 0.04 times 500 is 20. So then I could move that over if I wanted to. So like negative 20 equals 12.4 V. So I'm just subtracting it from both sides and then divide by 12.4. And I get a V of negative 1.6 meters per second. Okay. And now it makes sense that it's negative because the way I've drew it is the gun's going to the left. Bullet's going to the right, which is positive. Gun's going to the left, which is negative. My answer should come out as negative. Okay. Now, okay, so the gun has a spring in the stock that increases the amount of time. What impact force does the spring supply, and what would it have been without the spring? So if you've ever shot a gun, there's a lot of recoil, depending on the gun. Some guns don't have very much recoil because there's a big spring in the butt. Like my brother-in-law is an ex-Marine, and he showed me his gun. I was like, oh, and well, we went shooting, and then he's American, so we went shooting. And I shot the gun, and I was like, wow, there's like no recoil. And then he like took it all apart in like 2 seconds and showed me this massive spring in the butt, and it was really cool. So in order to answer this, we need the impact force. So we're going to go M delta V equals F net times T. Okay, so and it's the mass of the gun that's shooting. So its initial velocity starts at 0, and then it goes to 1.6. So we have 12.4 times 1.6. You don't have to worry about negative positive here because we're just finding an absolute value, equals F times, and then we'll go without the spring, 0.04 first, and then we'll do it with the spring. So 12.4 times 1.6 is 19.84 equals 0.04 times F divided by 0.04. That's 496 newtons. Okay, but with the spring, 19.84 equals, we're going to change that time to 0.6 times F. So 19.84 divided by, 4 divided by 0.6, and you get a force of 33 newtons. So even a little bit of absorption, you're changing the force quite drastically. Okay, and that's the whole point of absorbing and increasing the amount of impact time. Okay, big theme in this unit. Okay, this one's a little bit trickier because now we're dealing with vectors. A stationary 4.2 kilogram watermelon is blown apart into 3 pieces. So we have Pi equals P1 plus P2 plus P3. Okay, and because Pi is 0, because it's stationary, then P1 plus P2 plus P3 has to equal 0. Okay, now this is going to be key for us because if you add all the vectors together, you're going to get 0, just like we did in equilibrium. Okay, so the first piece is going up and to the right at an angle of 64 degrees above the horizontal. So that's going to be, excuse me, where's the other piece going? Down and left. Okay, so it's going something like that. And that's going to be 1.7 times 6.8. So that's 11.56. And this angle right here is 64 degrees above the horizontal. The next piece is 1.4 kilograms and heads down and left. Oh, crap, that sucks. I'm going to put this on this side. Down and left 27 degrees. I'm supposed to be right, I think. So it's going this way, and it's 1.4 times 4.5. 1.4 times 4.5. 6.3. So it's going to be smaller than the other one. So something like that. I actually don't know which way it's going, but that's okay. 27 degrees. And so then the other piece will do something like that maybe, I don't know. Yeah, so it could be, what I'm trying to say is it could be like this, where it's going that way, or it could be like that. It's kind of an ambiguous case. But we don't have to deal with ambiguous case for this because it'll be solvable without it. So if you think about this first vector, which is 64 degrees right here, that means it's 64 degrees right here, 64 degrees, that whole thing. And then we're adding a vector like this, where this is 27 degrees, which makes this interior angle 64 minus 27, which is 37 degrees. Okay, and so that's what makes it non-ambiguous, because we can actually use trig to solve for that angle. Okay, so now we can just do cosine law again. So 11.56 squared plus 6.3 squared minus 2 times 11.56 times 6.3 cos 37. So 11.56 squared. Okay, and then we get this side. So this is P3. P3 equals 7.55 kilograms meters per second. Okay. We're trying to find the velocity, which means we need the angle. So I'm going to find this angle right here. So sine theta over 6.3 equals sine 37 over 7.55. So 6.3 sine 37 divided by 7.55. Second sine. Hopefully this works. Okay, this theta is 30 degrees. That should make sense. I think that makes sense. And then we want to know the velocity. So this is kilograms meters per second. So I'll apply the angle in a second. So we have 1.7, 1.4, and it was 4.2. So 4.2 minus 1.7 minus 1.4. The last piece is 1.1 kilograms. So we're dividing by 1.1 kilograms. 7.55 divided by 1.1 is 6.86 meters per second. So that's our VF. And then if this is 30 degrees and this is 64 degrees, that means the whole thing is 94 degrees, which means that we're actually going that way 4 degrees west of north, which I hope makes sense. So just to double check that, because I'm not quite sure which way it goes, I want to know which way my x momentum is going. So if I add all my x momentums together, I should get 0. So if I'm going to go, so I can go 11.56 cos 64, that's this line right here, minus 6.3 cos 27. Okay, and I'm just going to do that. 11.56 cos 64 equals minus 6.3 cos 27 equals, and I get a negative answer. So this is a negative answer, which means that my final momentum is going to the left. Okay, and so that means that it's definitely going west. Okay, and then like pretty obviously 11.56 sine 64, like that arrow is going to be a lot bigger than that arrow. So it's also going up. So I know that this is correct. Okay, so you can always double check using your components. Hopefully that makes sense. Okay, 2 more examples. A battleship, so like a boat, has a cannon facing towards the front of the ship that is at an angle of 12 degrees above the horizontal. Okay, the total mass of the battleship is 4 times 10 to the 6, so 4 million kilograms. And the cannon fires a 250 kilogram shell at a velocity of 780 meters per second. What will the boat's change in velocity be upon firing a shell? Now, if you think about the boat, so here's the boat. It's underwater a little bit. Okay. Here's the, I'm just going to draw like a stupid boat. Okay. Here's the, I want it to go this way. So here's the cannon. Okay. It's going to shoot a shell that way at an angle upwards. Now, if you think about the change in velocity, the boat is probably going that way, which means that I only care about the change in velocity going that way. Okay. And so what I have in this case is, and you don't have to know the initial speed of the boat, because whatever the velocity comes out as, that's going to be how much it changes. So it doesn't, you can just treat it as 0. So let's say the P initial is 0. So if you think about it, we have a momentum going this way, like that's our P2F, which means that our P1F has to be this way. Okay, because it has to equal 0. But all I care about is, let's draw it this way. P1F is this way. All I care about is this and this. Okay, so instead of dealing with my momentum as angles, I'm going to say P1 initial x is equal to P1 final x plus P2 final x. And I'm defining P2F as the shell and P1F as the boat. So, and all I'm doing is splitting it into components because I don't care about the vertical at all. Okay, if I had said something like, well, I could apply some kinematics to this and tell you how long it takes and its initial velocity and all that stuff, and then you could say, okay, how far does this boat sink in the water when it shoots a shell? But we're not going to do that, because sinking would be in the y direction. Okay, so this is 0, and then P1Fx, this is the boat, so we have 4 times 10 to the 6 times v plus P2Fx. Okay, so this is going to be, it's 250, so mv, times v, 780. But again, it's only in the x direction, so that means I'm going to go cos 12. Okay, and then, like, this is technically vx. I'm not actually, there's no angle here or anything like that because I'm already splitting it into x's. So 250 times 780 times cos 12. So we have 4 times 10 to the 6 Vx equals, because they're going to be equal, 190,739. And then I'm going to divide that by 4 times 10 to the 6. And I get Vx is equal to 0.05 meters per second. Okay, it's going to be very, very small because the boat is very, very large. Okay, but what you need to understand here is that it's only in the x direction. Okay, the boat is moving in the x direction. The change in velocity is going to be in the x direction. Okay, you're not doing both. Okay. Hopefully there's no questions. I'm not seeing anything in the chat. So, okay, last example, and this is an angled collision, but it's an inelastic one. So car A is 1,265 kilograms and is traveling 64 kilometers an hour towards the east. So this is going to be, they're sticking together. So we have P1I plus P2I equals PF. Okay, so the first car is going to the east. The second car is going north of east. So it's going to look like this. There's our first car. So P1I equals 12. Okay, so I need 64 divided by 3.6. So this is 17.8 meters per second. 82 divided by 3.6 is 22.78 meters per second. So P1I is 1265 times 17.8. So this is 22,517 kilograms meters per second. And then I'm adding the next Carbis potential. So that one's going to look like this. And so this is going to be 1400 times 22.78. So this is 31. I'm not going to do it there. Oops. 31,892. And this is 30 degrees. Okay. Now, this is P1 plus P2, and it equals PF. So it equals that. Now, keep in mind that this is M1V plus M2V equals M1 plus M2 times its final velocity. Okay, so that means that this line that I have here is, and this angle here is 150 degrees. This is going to be 2665 times V. Okay, because it's both masses together. So again, cosine law. I'm getting tired of cosine law. 22,517 squared plus 31,892. These are some big numbers. Okay, so this side is 52,611 kilograms meters per second. Okay, that's what our PF is. And so we're going to take that, and we need to find this angle as well. So let's find the angle first. Sine theta over 31,892 equals sine 150 over 52,611. 31,892 times sine 150 divided by 52,611 second sine. Okay, so theta is 18 degrees. And so we're going to take the 52,611, divide it by 2,665. Okay, I'm adding 1,400 plus 1,265. And I get a VF of 19.7 meters per second, 18 degrees north of east. Okay, so if you think about it, all of the north aspect of the final momentum comes from car number 2, car B. And what's happening is that north aspect is staying the same, but our east aspect is getting much bigger because we have car A plus the east aspect of car B. And that's why the angle becomes 18 rather than it becomes smaller than 30. Okay. And notice how our speed is getting faster because they're both headed in the same direction, kind of. If I had made the car B go west and north, then it would slow down a lot. Okay. Hopefully that's good. Are there any questions? You can put them in the chat. No, nothing. Okay, so for today is you can keep working on the worksheets. You can do the provincial exam questions, and then tomorrow we'll go over all those. I ask that you double check that you've handed everything in. So we have the vector quiz, the equilibrium test, and the energy quiz. So just double check if it's not on OneNote, maybe just send me a message saying, hey, this is where it is, or resend it, or try to resubmit to OneNote because it's way easier when it's in OneNote. Other than that, that's all I got. So if you have questions, just message me and I'll try to answer them the best I can because apparently I can't hear you guys. So that's it for now. So have a great day.